Assalamualaikum warahmatullahi wabarakatuh. Kita pakai bahasa Jawa aja ya. Saya berterima kasih kepada panitia, terutama Pak Markus, dan saya berterima kasih pada adik-adik semua yang sudah mau datang. Mudah-mudahan we can learn something together from the expert today and tomorrow. Today I'm going to present to you about a synchrotron-based high-energy optical conductivity on heterostructures and strongly correlated electron systems. There is a new phenomenon in the thin films. It's very fascinating, at least in the past 15 years, in which you can create a metallic sample from non-metal thin films. It's really impressive the way how nature works, and it's very much something that we probably want to do in the future. I give you one example today about lanthanum aluminum O3 and strontium titanium O3. Ya. Ada yang sudah pernah dengar bahan ini? Lanjut tangan. Belum pernah dengar? Pernah atau belum pernah? That's very good. Some of you know already. Many of us don't never hear this one. So let me ask you these questions. Lanthanum aluminum O3. And look at the crystal structure. These are the crystal structure. Can you see it? These are the crystal structure, which you have the lanthanum in the corner there, and you have the aluminum in the middle, and you have the oxygen center down. Okay? The interesting part, let me ask you this question, is the wrong direction. The electrical properties of the lanthanum aluminum oxide, is that a metal or insulator? Who say insulator? Metal or insulator? No idea. It's actually, these are insulator. Yeah, with very wide band gap, above 5 electron volt. Yeah. So the optical band gap is above 5 electron volt, that we already answered it. Do you know, is that a metal or is that non-magnetic or ferromagnetic material? Do you know that? It's non-magnetic. Yeah? So the LAO itself, because with LAO, lanthanum aluminum 3, is insulator and non-magnetic. One interesting phenomena about this lanthanum aluminum 3, we call with a polar system. Yeah? Polar system means if you look at this as a layer by layer, lanthanum, there's one layer, and then there's aluminum, lanthanum with the oxygen, there's another layer, and we have lanthanum aluminum oxide, another layer. So this consists of additional hole in it, or missing electrons. So you have one plus layer. This side you have negative, you have excess electrons in the layer, and the other one you have positive charges. Right? So if you look at this, positive, negative, positive, what do you have in mind right now? It's a battery, right? It's a battery, you have positive charge, negative charge, positive charge, negative charge. So you can actually, if you can do that, you can actually combine this positive, negative charge, really precise. You can have very strong battery, only within a unit cell that is nanometer size. Yeah, but nature doesn't allow you to do that easily. So there's a way to compensate what they call the polar system, and this polar system might create you completely new physics phenomena. The way the nature works, how to compensate the polarization divergence. Yeah, it's Gauss law, it's a Maxwell equation, part of the Maxwell equation. So then you look at another material, lanthanum aluminum 3. The crystal structure very much similar. Look at this. The only difference is that you have, in this case you have strontium, in the other side you have oxygen in the middle. On the other hand, you have titanium in the center. This part you have aluminum in the center, right? But the crystal structure is very much similar. It's a cubic structure. Okay. But now look at carefully what happened. This material also insulator. I'll give you the answer right away. The optical band gap is still questionable. There's a lot of debate in the past, but I'm going to give you the answer. The optical band gap of strontium TiO3 is 3.7 electron volt. That's the first excitonic band, excitonic state, by the way. And then you have, again, this is also non-magnetic in nature. And if you look at these, whether this polar or non-polar material, if you look at these are zero, there's no excess electron, there's no excess electron, there's no excess electron. This is what we call with non-polar system. Right? So you can have the same crystal structure and change the element. You can create polar versus non-polar. That's the physics we can learn today. How this polar system, if you integrate, if you place this polar system into non-polar material, the behavior might become a metal. And it's only a few layers, it's only at interfaces. So how does it work? So what happened in the group by Harold Wang that was discovered around 2004, and Manhart from Germany, and a Villery group, that's Triscon group from Switzerland. What they discover very fascinating. So they grow layer by layer. So they take strontium, titanium, or 3 is what we call the substrate, and they put an atom, put it on top on the STO, and then they grow in total what's called with lanthanum, alum, or 3. And see what happened once you do that. Again, this is only atom by atom. You don't pull it everything there, but put one atom on top of another. And then they can count, they can measure the sheet conductivity, which is, you can imagine this resistivity or conductivity, inverse conductivity. If the sheet conductivity is 0, that means insulator. There's no charge carrier over there. Right? Think that one. If the sheet conductivity increase, that means towards a metal. Right? So take a look at this. This is the number of unit cell of lanthanum aluminium 3, the polar material, as a function of the sheet conductivity. 0 means there is no polar LAO, and then they increase to 1 unit cell, 2 unit cell, 3 unit cell, 4 unit cell, and etc. And 1 unit cell again is about 4 angstrom, 4 to 5 angstrom, and much less than nanometer. So if they do that, so this is at 0 LAO, they got this 0 conductivity. They increase the number of LAO into 2 and 3 unit cell. They remain insulator, right? Because everything remains 0. But check what happened when you add another unit cell of LAO. The conductivity jump up tremendously. From 0 to something, and this is 2 times 10 minus 2 times 10 to the 13 electron per centimeter. Right, the area. So when they increase the number of unit cell into 16, the conductivity remains there, but flat. It's almost the same. Right? So this fascinating phenomenon that was discovered around 2004, and this was a big hit in the Oxide community because probably we think of the new material for new energies, for instance, or even new devices, because things happen at interfaces. So the questions that we would like to understand, the field would like to understand, there's 4 important observations. First, there is so-called insulator metal transitions. Look at this insulator to metal. That's what we call with insulator metal transitions as a function of thickness. And then a sharp transition, look at this. Only 1 unit cell, only adding up 1 unit cell. You add another lanthanum, you add another aluminum, and then you add another 3 oxygen, it's become a metal. And it's not happen in nature. And the next one, even though you add more layers, it remains constant. And this number of electrons, the number of sheet conductivity here, that proportional to about 0.05 electrons involved in transport measurements. That's what we want to understand. Can we understand such a phenomenon? Yeah. So to understand that, I need to construct a new experimental technique, because it's not easy to measure interface. It's not easy to measure surface, right? So that's where we're gonna use so-called synchrotron. Have you heard about synchrotron before? Have you heard? Do you want to know? Okay, we do it next time, right? Not today. So we have the Singapore synchrotron light source, and that's really ideal to look at phenomena related to the surface and interface because of the energy ranges. So we construct a completely new beamline, what we call the beamline. So the distance from that corner to that point, for instance, about 10 meters. So it's very long distance with pipes everywhere. So we construct from zero. So if you like design, you can do experiment. You can come being a physicist and become like art and design, because you can do whatever you like over here too. But the key here is that you can have the photons, tune the photon energy from electron volt, 1 or 2 electron volt, all the way to 1,500 electron volt. So you can scan almost of elements. Look at the elements of periodic table you have, you can really scan it and pin which element does something in the material. Okay? So this work, I've done it with my postdoc, Dr. Yao Chao Zheng and Yu Zhejiang. So it helps me, and it took me 5 years to really develop, construct the beamline itself. It takes a lot of times when you do research. So this is the result. Yeah. So we grow the films. We do what we call with the pulse laser depositions. Yeah. So you really hit the targets what you have with the laser, and there's a pump coming out, and then you get one atoms and atom on the substrate, and you measure that, you characterize that as function of thickness extension. There's a fringes coming out from, you read pattern. So the work done with my PhD student, this is Teguh, he's from Indonesia, and collaborate with another PhD student I have, Anil. And the work done also together with Ariando, this is my colleague, and Venki Venkatesans, when we look at carefully the quality of the films. Look at this material, look at this data. Now we need to learn how to look at the data carefully. So if you look at this, reflectivity, what you want to measure is electron. One way to measure electron is to measure reflectance as a function of energy. So the y-axis here is reflectivity versus photon energy, right? So then you make comparison. This is bulk STO, bulk LAO. Remember, bulk means without adding up both materials, so it's independent material. And then you have 2-unit cell, 3-unit cell, 4-unit cell, 6-unit cell of lanthanum, molybdenum O3 on strontium, titanium O3. Right? So you really control that number of units. And remember, once again, if you look at this, if you do not do experiment without the synchrotron, if you do a regular experiment, it's very hard to distinguish between 2 and 3 unit cell and 4 and 6 unit cell. Remember, what you want to understand is that 3 and 4 unit cell, 2 and 3 are insulator, insulating material, and 4 and 6 are a metal. So we want to understand how to explain these are insulator and these are the metals. Right? But then you scan the energy. You do the experiment, you do reflectance measurement all the way, and you scan up to 35 electron volt. It's a huge number there. Then you can see surprising huge difference in reflectance measurement between around 15 to 20 electron volt. Look at the spectral weight here, what we call the intensity. So if you look at the intensity here, 2 and 3 unit cell are down there. And look at this, 2 and 3 green color and blue color are down there. And 4 and 6 unit cell is out there. So as soon as there's a metal in the material itself, there's a jump of reflectivity, but the jump of the reflectivity is not down here, but rather up there. That was missing. So for about 10 years, people doing research, LAO, STO in this field, they missed this structure, this metal insulator transitions. Yeah? So we have a problem in the past to explain it. Now you can explain it, the phenomena, where this electron coming from in the interfaces. Right? Because to begin with, they are both insulator material. Yeah, to begin with. Then you can extract. Physics student, you should be able to extract the optical conductivity. Yeah, take a look, the Maxwell equation that you're going to learn. There's an optical conductivity you can extract, and if you integrate the optical conductivity underneath the spectrum, then you are getting the number of electrons in the system. Right? So you can precisely telling, oh, there's a 10 electron there, there's a 5 electron per unit cell, or there's a 20 electron per unit cell. You can tell that so precise if you identify the spectra weight properly. Right? Now we do that. We integrate the spectra weight. Yeah, we integrate the spectra weight of reflectivity, and then we can find out the origin of the metal for 4 and 6 unit cell of LAOST. Okay, so take a look what happened. It turns out that, again, this is the number of LAO per unit cell, and this is the number of electrons per unit cell for individual. This on the top part is the number of electron of LAO with respect to bulk LSO. Yeah? And the bottom part is the number of electron in the interface of LAO-STO with respect to STO itself. So if you look at 0, that means there is no change in number of electrons. If you get positive value there, that means there is additional electrons which is coming from somewhere. It has to come from somewhere. Yeah? And you cannot just steal electron. If you steal the electron, then you go to jail. Yeah? You cannot steal the electron. You have to go to somewhere or come from somewhere. And then the same thing with STO. If you look at 0, almost 0 means there's nothing changes in terms of number of electrons in STO interfaces. Right? So what really surprising result is that look at the green color here. The green color is the number of electrons in STO, but only at interfaces. In which for 4 unit cell and 5 unit cell and 6 unit cell, there is additional electron, about half electrons. That's give you the metallism, the metals. And there's additional electron at STO interfaces. Where is that electron coming from? It turns out those half electrons are coming from LAO layers on top of it. Remember, you have lanthanum aluminum O3, which divided by separate layers, lanthanum LAO or ALO layers, and each of them contribute almost about quarter electrons per unit cell, and each of them provide electron into or transfer electron into the LAO-STO interfaces. Right? Now we know the phenomena. We can create any material becomes metal to insulator based on the charge transfer. We can force the electron to move from one side to another side. Yeah? The question is that how to force it? Why this electron move from LAO to the STO? This technique, the same time, we also able to explain what so-called we can also detect what so-called vacancies. Yeah? Like stoichiometry of your material. In this case, as it turns out, for 5, 6 unit cell and above, where the sample are metal, it turns out there is so-called oxygen vacancies. The surface of LAO, the oxygen tends to remove out from the samples, and that release an electron back, and the electron from that surface going toward to the interface to compensate the polarization divergences. Yeah? So it's very interesting phenomena in physics, and yet very simple to explain if you are able to calculate, to measure the total number of electrons. Right? And the same thing with other semiconductor, you can use the same technique too. Then we also find out more than that, that for insulating samples, there is still electron moving from one side to another side, but the electron is moving within the layers. Yeah, within the LAO itself. If you look at this, the electron is moving from the red color to the blue color, and the electron from the red color move to down there, and etc. etc. Yeah. So in nature, this doesn't happen. It goes differently. Right? So what does it mean? Now I can make, for instance, a device, yeah, completely different device now, based on only simple number of layers. I can create metal in this side and insulator on the other side by adding one layer and create oxygen vacancies. And I can put it back and become an insulator if I put the oxygen vacancies back. Yeah, put the electron back or put the oxygen back, then you can create so-called insulator metal transitions. And this work was then, it is very interesting story that at the beginning, when you do the experiment, when you analyze the data, you need to make assumptions, right? So if your assumption is not correct, the whole analysis becomes also not correct, right? So our work being reviewed and being quite at the beginning was challenged by a group in the United States and Germany, and it was very lucky that what they mentioned here that in our what is this? I cannot see this. In our present work, yeah, they're using in situ ellipsometry measurements. They actually confirm all the assumptions made by our group, yeah? And they agree with the analysis that there is so-called spectral weight transfer from the LEO into the STO and the change of the electric constant. So it's very important it's also very important that once you publish results, something, yeah, other people will try to find out whether that's correct or not because they're interested in science. Yeah, that's what Graham mentioned this morning. They want to find out what happened to the polycrystal sample, right? It turns out it's not that high at the moment. And that's become questionable with the thin film sample, right? So there's something that if you want to do research, do it properly because other group might come and chasing your result too. So anyway, so we look at that phenomena because once you do experiment, you also want to build up a model, a theory. Yeah. So this one, in my group, we also doing theoretical calculations. So June is my PhD student, Yang Ming is my postdoc, and we collaborate with George Sawatsky and Yuan Ping Feng to calculate whether the phenomena that we explain is consistent with the band structure, for instance. Yeah, band structure calculation. So we look at that carefully. We extract the whole experimental what has been done in the past. Look at this, all these experimental things, yeah, from transport, XRD, high energy optics, and etc. etc. When we categorize them, and then we put them into a picture, a model. And your model, the model has to be able to explain the experimental data. So what we found that if we only have 2 and 3 unit cell where everything remains insulator, there is so-called buckling, so-called lattice distortion right in interface. And the lattice distortions compensate the polarization divergence in the LAO. That's the way the nature or the thin films try to compensate the polarization divergences. But as soon as you put 4 unit cell, buckling is not sufficient to compensate the polarization divergence in it. Yeah, the buckling, the lattice distortion is not good enough. It's not strong enough to compensate the polarization divergence. So what happened is that then we calculate the total number of energies. What happened when we increase the number of layers? As it turns out, when you increase the number of layers, the oxygen on the surface tend to release from the sample. And that's way, when the surface of the oxygen comes out from the surface, yeah, the buckling reduces. Yeah, no buckling anymore, and the insulator metal transition is due to the oxygen vacancies at the surface. So look at, now you can really see that when you do physics, you really need to have a good chemistry. Yeah, because everything related to the stoichiometry, you really need to understand that properly. And that's whatever you do. For instance, if you make thin films, you really have to consider the surface before you think deeper what happened in the interface. Yeah, because even though they are very thick samples, surface still connected very nicely with the interface through this phenomena, so-called charge transfer phenomena. So we are able to explain the whole experimental data, available at that time from a different type experiment, and then we are able to construct a model to explain it based on the band structure point of view. Yeah. Now you are ready to go for the next step. Can you really control oxide vacancies now? How to control release? If you can do that, you can create the same layer, 3-unit cell, 4-unit cell, and some part you pull oxygen out, some part you put the oxygen back. You have metal sort of metal transition. Yeah, you can make very nice PN junction, PNP junction at the end of the day too. So in the end, what we want to have is to replace the current semiconductor. Right? That's our goal generally. So to summarize what happened, yeah. So the interplay of electronic reconstruction, lattice distortions, surface oxide vacancies is responsible for insulator metal transition in the LAO-STO. The second part is that we show the potency of high energy optical conductivity. So this is new technique that we develop to construct, so we are able to really measure what's so-called the spectral weight transfer and various type of vacancies in the correlated electron system, but also various type in the thin films or 2D materials as well. So you can actually apply this technique, but it's a very simple technique. It is very interesting for physics point of view, because what you need to understand is a Maxwell equation to begin with. Right? But that's not the end of it. How many minutes do I have? 5 more minutes. All right. 5. All right. Okay, I have 10 more minutes. So, but you always need to criticize your result. Yeah, it's very important that you criticize the result. So what we found that the high energy optical conductivity measure 0.5 electrons. Okay, that's the technique, the optical conductivity, the reflectant technique that we show you. Transport, on the other hand, measure only 0.05 electrons. So there's a missing of 0.45 electrons, right? In science, you have to find out where this electron goes at the end. Yeah, it cannot just disappear. Otherwise, you cannot explain the phenomena properly, right? So we look at carefully. So then the next question, how to explain such a discrepancies? Look at this STO. What happened with STO? That is the question itself. Yeah? In the past, if you read literature, STO, or what we call with STO, strontium titanium O3, they call with a passive material. Passive material means that it will just stay there, it won't disturb anything on top of it. And that was a passive material. We want to find out whether that really is a passive material as what believed for 100 years, for example, 50 years, whatever, many years in the past. So what's going on with STO? And then the first thing you need to do is read the literature. Yeah, you read everything down there. Go back to 1965 papers. Where were you in 1965? Student. Where were you? Ada di mana, Mbak, tahun 1965? You don't know? Alright, I don't know either because I wasn't here at the time. Yeah, so you go back to 1965 papers and read all the way to 2008 papers. So what we found, yeah, you read all the literatures, 50 papers and everything. What we found that there's a discrepancies in previous optical spectroscopy studies, particularly near its characteristic in the STO, strontium titanium O3. So there's a different result from one experiment to another experiment, right? So you get really confused, right? So what happened yesterday we learned, when you're confused, you must be happy. You should be happy now because you have a job to do now, right? So something new should happen. But all this paper, yeah, agree, or at least one of the papers state that existence of excitonic effect had been explicitly mentioned to be absent. That was physical review letter in 1970, and this was referred to many papers until before our publication comes. Yeah, it was absent. Exciton was absent, and exciton itself having electron-hole interactions. And some of the exciton, what we call the resonant exciton, even having electron-electron and electron-hole interaction. That is the consisting. And if that happens, you cannot call the STO as a passive material anymore. We want to find out if there is electron-hole interactions strong enough or to create the exciton in STO. Yeah? So the conclusion was that from the literature studies, very confusing, and no one has done or published temperature-dependent spectroscopic ellipsometry in the broad energy range. So it's a good thing to do something. Yeah. So then with Pranjal is my PhD student, Paolo Trevisanotto is my postdoc, Daniel Schmidt is my postdoc, and Lorenzo is my postdoc. We collaborate with Valerio and also with Shinichi. So we perform some experiment to test our result with facility in Japan, and we want to make sure that everything reproducible. And then we look at carefully just strontium titanium orthene, something that has been studied for more than 60 years. But this time we want to find out what we call with exciton. Yeah, see whether the exciton is really absent. Then we look at carefully again the optical conductivity. This is the epsilon 1, epsilon 2. Yeah, this epsilon 2, the real part of optical conductivity, and this is the imaginary part of the optical conductivity. And then this is the differences between the real part and that is the imaginary part as a function of temperature. Yeah? And then we perform the theoretical calculations. So experiment 1, 2, 3 are experimental data, and then compare with theoretical calculations. What is really interesting is that if you look at this structure, there's a very sharp structure. There's a very sharp structure in the absorption part of the difference in the optical conductivity, and they change dramatically as a function of temperature. Okay? And this structure was missing for all the experiments in the past. They never measured. All the experiment was done below what's so-called 3 electron volt. Yeah. And then we look at, then we calculate. You can calculate the optical conductivity. You can calculate the dielectric functions, real part, imaginary part, but this time you explicitly include electron, and electron-hole interactions through, for instance, GW beta salvator equations. You can do that. Yeah? So now you can see between the red and this black color, red and black, the black color, it was assumed to be no exciton at all, or there's assumed that there is no electron-hole interaction in STO. Yeah? That was our knowledge in the past for many years. And now we include the electron interaction. If you do that properly, you have the spectral weight shift dramatically to low energy part. And that spectral weight, if you look at the sharp structure there, is very much close or even on top of the temperature dependent of the sharp structure in the difference of optical conductivity epsilon 2. Right? So now we understand something that when we look at STO, it turns out we really have to consider what we call with the correlation in STO, electron-hole interactions. What does it mean then? What it means that if you place something on STO, you place whatever thin films, you place graphene for instance, or you place two other 2D material, it might change dramatically the optical conductivity because of the correlation. Right? So we test our knowledge. We challenge if our knowledge is correct that STO have the electron-hole interaction, place graphene on it, the optical conductivity of graphene should change dramatically as well. So we did that. Yeah? So we did that experiment now again with my postdoc Iman and Pranjal, and this is Iman was my postdoc. Now he is the Gajah Mada University, Iman Santoso, and Paulo Trevisanotto and Yang Ming was my postdoc, and Loh Kian Ping, my colleague from chemistry, and this is Antonio Castro Neto, one of the pioneer in the graphene research, theoretical calculation. So we look at graphene. We place graphene on strontium titanium orthene. The idea is that how big the change is, how big the change of the optical conductivity of graphene because of the correlation effect. Now look at the result directly. So if you place graphene, yeah, look at this result. This is graphene on silicon dioxide. Right? This is very important. If you want to tell your graphene, a really freestanding graphene, it should look like this. This is what we call with the resonant exciton. You must have this. Yeah. So if you don't measure this resonant exciton or change in graphene, also change dramatically what happened in resonant exciton. Now if you place graphene on strontium titanium 3, look at the structure, the blue color here. There's this peak missing now, disappear, completely disappear, yeah? And the force spectral way toward low energy. Yeah? This enhancement tiny little bit there, but the interesting part is that you can really make the graphene become transparent, yeah, in the UV because of the interactions with strontium titanium. So it's really amazing phenomena that correlations, electron-hole correlation in STO change dramatically what happens with the material on top. Okay? So to summarize the talk that we have, what we learned today is that, hopefully we learned today is that electron-hole interactions yield to what's so-called anomalous exciton, what resonant exciton. And as it turns out, they are very important for the electronic structure, electronic band structure of the strontium titanium 3. So I would like to warn everyone that be careful with any statement by saying STO is a passive material. It's not a passive material. And then you can also study with the same technique. Now we can also study other type of substrate, but you think, yeah, it's only doing nothing on the whatever material on top of it. Now, the reason is that because the future technologies that we would like to have is that very thin layer, 2D material and everything, and that has to be placed on something, right? So you cannot just hanging around. So, to summarize also that we present you the potency and new technique, so-called the high energy optical conductivity, to reveal exotic phenomena, new phenomena, yeah? In oxide, for instance, heterostructures, and correlated electron system in general, and the methodology present here is applicable to many types of samples, including the nanomaterial as well. Thank you very much.
Thank you. Please give applause for Bang Rusdi. Okay, thank you, Bang Rusdi, for interesting presentation about LEO and STO.